Let A be this 3 cross 3 matrix, and for some theta belonging to 0 to pi, A square is same as A transpose. Then we have to find the sum of diagonal elements of this matrix A plus I raised to 3 plus A minus I raised to 3 minus 6A. Now, this is a very interesting problem from one important type of matrix, that is orthogonal matrix. Now, in case of orthogonal matrix, generally we learn the basic definition of orthogonal matrix, that a matrix is called orthogonal matrix if A into A transpose, that is identity matrix, right? If you multiply a matrix and its transpose, and if the result is identity matrix, then we say that this matrix is orthogonal matrix. However, this definition is not that much useful when we have to identify whether a matrix is orthogonal or not by observation, right? In case of orthogonal matrix, I mean, this is the definition, that A into A transpose, if that is I, then matrix is orthogonal. But the problem with this definition is that only after calculating A into A transpose, uh, you can identify whether the matrix is orthogonal or not. That means first we need to find A into A transpose, and if that is identity matrix, then only we can claim that it will be orthogonal matrix. However, if you are familiar with properties of orthogonal matrix, then simply by observation you can tell whether a matrix is orthogonal or not. So there are two important properties. The very first one is that in case of orthogonal matrix, every row is perpendicular to every other row, right? If you take any row vector and if you take the dot product of that row vector with any other row vector, then you should get a 0, right? For example, here let us say this is R1 and then this one is R2 and finally this one is R3. Now here if you take R1 dot R2, let us say R1 is this vector where we have cos theta, 0 and minus sin theta as x, y and z component. So if I take R1 dot R2, then we should get a 0. Clearly you can see cos theta into 0, 0 into 1 and then minus sin theta into 0. Or if you take R1 dot R3, then also the result will be 0. Right? You can take any one row and any other row, and those two row vectors, they are perpendicular vectors. That means their dot product will be 0. You can take R1, R2, R1, R3 or R2, R3. And same thing you can say for columns also. That means first column C1, this is perpendicular to C2, right? First column C1, this is perpendicular to C3. And similarly, second column C2, this is also orthogonal to C3. Hence the name orthogonal matrix. In case of orthogonal matrix, every row vector and every column vector, they are perpendicular to every other row or column vector, right? R1, R2 are perpendicular, R1, R3 are perpendicular, and so on, right? So, and also all the row vectors and column vectors, they are unit vectors. That means if I take vector R1 dot R1, then the result will be 1. Same thing you can do for R2 dot R2 or C1 dot C1. For example, here R1 is cos theta, 0 and minus sin theta. If I take the dot product with itself, then we'll get cos square plus sin square, which is 1. So if you are familiar with this property of orthogonal matrix, then by observation you can tell that matrix A is orthogonal matrix, and that will imply that if we have orthogonal matrix, then it means A into A transpose, this must be identity matrix, right? So here it is given that A square, this is same as A transpose. Now if A square is A transpose, you can multiply both side by matrix A, and then on left hand side we have A cube, and right hand side will be A into A transpose, which is identity matrix, because the given matrix is orthogonal matrix. And now the problem becomes much easier. We need sum of diagonal elements or the trace of this matrix. Now let us say this matrix is B. So first we are going to simplify this matrix B, and then we'll calculate trace of matrix B. And for simplifying, we can use A plus B whole cube formula. So this matrix B, this will be, and because these are commutative matrices, we can use those binomial theorem, binomial expansion of A plus I raised to 3. So this will become A cube plus 3A square plus 3 into A plus I. Remember, generally matrix multiplication is not commutative. That means AB and BA, these two are not same. And therefore, we cannot use the standard formula of A plus B square or A plus B cube and so on. But if one of the matrix is identity matrix, then it becomes commutative. A into I, this is same as I into A. And therefore, we can use those formula of A plus B cube or A plus B square and so on. So this will be matrix A plus I cube. Similarly, A minus I cube, that will be A cube minus 3A square plus 3A minus I minus 6A. And now you can see that 3A plus another 3A minus 6A. So these three will cancel. 3A square minus 3A square will cancel. I and minus I, these two will cancel. So basically matrix B, this is twice of A cube, and A cube was same as I. That means after simplification, this matrix B is nothing but 2 into I. We need a trace of this matrix B. So trace of matrix B, this will be twice of trace of identity matrix. And for 3 cross 3 identity matrix, sum of diagonal elements, there will be 3. So therefore trace of I, which is trace of I, that will be 3, and hence trace of matrix B, this will be 2 into 3, which is 6. So the correct answer for this problem will be 6. Now this was important concept because if you are familiar with this definition of orthogonal matrix, then simply by observation, you can identify whether a matrix is orthogonal or not. Otherwise, you will have to calculate A into A transpose, right? So always remember that in case of orthogonal matrix, every row is perpendicular to every other row. Same thing for column. And each row vector and column vectors, they are unit vectors. That means if you take dot product of row vector with itself, we must get 1. And also for orthogonal, you can remember one more result, that because A into A transpose, this is identity. In case of orthogonal matrix, A inverse, this is same as A transpose. Because if two product of two matrices is I, identity matrix, then each one is inverse of other. So for orthogonal matrix, inverse is nothing but transpose of the matrix, right? So for this problem, I mean, after simplification, matrix B was 2I, and therefore trace of matrix B, this will be 6. And that is the correct answer for this problem.